Good evening, everybody. It is my great pleasure and honor to introduce our speaker today, Professor Stanislav Dehaene, who is here on a joint visit and joint initiation of the Institut de France, the French Embassy, and the Israel Academy of Sciences. Professor Dehaene is a member of the French Academy of Sciences, and as I heard, he is one of the youngest members that were ever elected to the Academy for his significant achievements in brain research. Professor Dehaene received his training in mathematics at the École Normale Supérieure in Paris, then completed his PhD in cognitive psychology with Jacques Meller, postdoctoral studies with Michael Posner, and then he was he did neurological modeling studies with Jean-Pierre Changé. He has afterwards been working since 1967 at the Orsay Brain Imaging Center in Paris, where he directs the cognitive neuroimaging unit since 2001. In September 2005, he was elected as a full professor on the newly created chair of experimental cognitive psychology at the Collège de France in Paris. Professor Dehaene is the author of over 100 scientific publications in major international journals. He has received several international prizes, including the McDonald Centennial Fellowship and the Louis D. Prize of the French Academy of Sciences. He has published an acclaimed book called The Number Sense, which has been translated into 8 languages. He has also edited 3 books on brain imaging, consciousness, and brain evolution, and has authored 2 general audience films on the human brain. He is the associate editor of Cognition, which is an international journal of cognitive science. Stanislav Dehaene's interests concern the cerebral basis of specifically human cognitive functions such as language, calculations, and reasoning. His lecture today is on the subject of recent advances in understanding the brain mechanisms of consciousness. Professor Dehaene, it is a great honor and pleasure for me to introduce you and to have you as a guest in our academy. Please.
Well, thank you so much for your hospitality. It's a great pleasure for me to be here. My wife and I are staying in Israel for 4 months, and so we are discovering the amazing, I should say, scientific power of this country. And especially, I should say, neuroscience and cognitive science, where the forces are enormous. Tonight, I would like to speak about this topic of consciousness. And maybe you come here with a little bit of skepticism. What can science say about consciousness, you know? It's been one of these topics that you're not supposed to touch before retirement, basically. And I hope I'm still far from that. But I think that I would like to try to show you today that we have in fact a lot to say about consciousness from the brain point of view. Not maybe about the biggest picture that you would like about consciousness, but about specific meanings of the word consciousness. And tonight I will speak specifically about one of the meanings of consciousness, which is conscious access. The ability that we all have when we attend to an object to become aware of it. And there may be, for instance, a bottle on this table that you were not aware of, but now that I've drawn your attention to it, you became aware of it. Before you were aware of it, it was already projected on your retina, but you were not aware. What's happening there? Why is it blocked? What I would like to show you today is that we have a laboratory approach to consciousness. It's no longer a mystery. It's just a problem. It's a problem that we can attack because we have experimental paradigms that allow us to attack it. And some of the paradigms that I will be speaking about are on the screen right now. One of them, especially which I will demonstrate, is the masking paradigm, We can flash a word, for instance, or a picture so briefly, 29 milliseconds, that when it is preceded, and especially when it is followed by shapes on the same place on screen, you no longer see it. So we have a way to make a whole word disappear from your consciousness and reappear as well. Another paradigm is called the attentional blank. Is if I distract you for a brief period by a first target, like this letter in the middle of digits, then I may present a second letter, and if it's close enough to the first, you will not be aware of the second letter because you've been temporarily distracted. Very simple stuff, you know, we're not talking about the big philosophical issues of consciousness. I may return to them at the end. But we really want to have basic paradigms that allow us to distinguish between conscious and non-conscious processing of the same stimulus. So I want to make a demonstration for you of the exact paradigm that we've been using in the lab. I hope this will work. And it's a situation where we can make a digit completely invisible. So bear with me while the projector is changing resolution, because that's the exact stimulus we're using. So in this experiment, you have to fixate your eyes in the center, and while you fixate in the center, this is behaving strangely, I won't use it, you could see that there was a digit on the side, and then there's going to be a blank, and then there's going to be these letters around the digit. The letters are the mask. Your task is to try to see the digit and maybe to read it. Okay? So we'll vary the delay between the digit and the letters. We start with 300 milliseconds, and I hope you can see the digit perfectly well. It's 1, okay? And try to focus on this digit. It's a 6. I hope you could see it. And it will get shorter now. And you can still see it when it's 100 milliseconds or 66 milliseconds, 9, I suppose. Okay, 4. Again, now we make it even shorter. Okay, can you see it? Maybe the projector is not quite right? But I hope you get the idea that I swear to you the digit is still there on every single trial. It's there on screen. It's going into your retina, but you can't see it unless you blink or something like that. You can't see it because the letters are taking over, and somehow they're catching on in the brain and making the digit invisible. Okay? So this is one of the paradigms we have at our disposal, and of course if we make it exactly at threshold, then we can have half of the trials that are seen, half that are unseen. You can see the importance of subjectivity here. You are defining whether you saw the digit or not, and on every trial I can ask you, do you see it, do you not see it? That's an ideal situation because I can have the same physical stimulus, but half of the trials are conscious and half are unconscious. And we trust the subjectivity of the person, the watcher, because that's what defines the field. That's what defines whether there was or there was not consciousness. So we can ask several questions here. First question is, of course, how deeply does this unconscious subliminal stimulus below the threshold go in the brain? Can it reach a level of meaning, for instance, without being seen? Can the brain operate entirely without consciousness? Second, of course, is what is unique to conscious stimuli. Are there specific stages of operation in the brain that take place only when you are conscious? So what we can call signatures of consciousness. And we will search for that using behavior, like mental chronometry, how quickly you can respond to stimuli, but also functional MRI, which is a way to look at the active areas of the brain in 3 dimensions, so the cortex and subcortical areas, and also these techniques of time-resolved measurements of brain activity. I think this is especially important because we want to follow the stimulus in time as it gets through your brain, and these techniques allow you to reconstruct the electrical activity of the brain as well as the magnetic activity of the brain, magnetoencephalography, and in some cases we even have access to intracranial recordings with electrodes placed deep inside the brain for epilepsy monitoring, and we can use them with the patient's agreement, of course, and collaboration in order to track brain signals. At the end of my talk, I'll come to these special cases that are very interesting. If we have a science of consciousness, we can answer interesting questions. When do infants begin to have a conscious experience? What about coma patients, vegetative state patients? Can we say something about whether or not they are still conscious, even though they cannot respond? So I hope I'll get there at the end of the talk. So I've been doing about 15 years now of research on subliminal processing, trying to see how far a word like this word 9 here, which is masked and made invisible, how far does it travel in the brain? And one way to answer this question is to use a priming paradigm. So you make this word invisible, but then you follow it by another word, which is conscious, because it's presented for a long duration, 1/5 of a second. It's quite enough to see it. So you see this word, and you're told, for instance, to decide whether it's larger than 5 or smaller than 5 with your two hands, as quickly as you can. But then we can ask, is this word, which is unseen, influencing the processing of the word which is seen? It's called the priming method. And this has been really a wonderful technique to ask how far a stimulus travels in the brain, because with this technique, combined with brain imaging, we've been able to show that there is priming in the sense of facilitation of the processing of this visible word by the unconscious word at several different levels in the brain. First, in this example, it's the same word, right? You repeat the same word twice. So, do you get help from that? You do. You get help, you get a facilitation of about 20, 30 milliseconds. It occurs inside this area of the brain, the visual word form area, which is an area that I've studied a lot, which is involved in the orthographic knowledge of your brain. And so the orthography pattern of the word gets analyzed unconsciously, and you get facilitation when you have a sort of unconscious preview of the same word. But it doesn't stop there. And we found also that there is another area which is involved in quantity processing, which is in the intraparietal sulcus, so in the parietal lobes, left and right, more dorsally in the brain. And this area cares about the quantity. So you can get priming here because it's the same quantity which is being presented twice, once unconsciously, the other consciously. And you may even get priming, let's say, from 8 to 9, because they are close. From 7 to 9, it gets a bit smaller, and from 1 to 9, it's the smallest. Okay, so you get quantity-based priming. You can even get a little bit of a motor priming. So in this example, both numbers are larger than 5. Well, you can show that the hand cortex is already being primed a little bit by the unconscious word, gets pre-activated. So the conclusion of this study and many others has been that the subliminal stimulus travels through the brain. It doesn't get stuck subcortically, it doesn't get stuck into primary areas, it goes through the cortex quite far. And in fact, we have all this series of experiments showing that even the meaning of a word or a digit that you have not seen, that you have no awareness of its existence on the screen, makes its way to the meaning level. For instance, maybe just to take the example on the bottom here, a word that conveys an emotion, like a word like rape, maybe, will travel all the way to your amygdala, which is a center for emotional processing. And the meaning of the word as an emotion word will be encoded there without your consciousness. So now we have to ask what's special about the conscious processing. And this is what I want to talk primarily about in this lecture. What happens when the digit crosses the threshold and suddenly you see it? Is there something special or unique that's occurring in the brain? So in order to study this, we use this paradigm that I showed you at the beginning. We flash a digit, we vary the delay, and by varying the delay, we make the digit more or less visible. And we're going to ask what can a subject do with it, and how do brain activations vary as a function of this delay. So here in this experiment, we ask subjects to compare the digit with 5, and we also ask them to tell us, using a cursor, whether it was visible or not. And they can use a continuous cursor to say that it was not seen, a little bit seen, better seen, and all the way to complete visibility. It may sound a little bit paradoxical that we ask subjects to decide whether it's larger or smaller than 5, when sometimes they have not seen it, but that's the whole goal, right? We want to have a sort of forced choice and to see how far they can go with it. So the first thing, very simple, is what is your behavior? You experienced that before. This is a function of the duration between the digit and the mask. This is what we call the visibility function, and this is the objective performance function. How well can you do in deciding whether it's larger or smaller than 5? You can see that both curves have a sort of threshold. They have a non-linear part in the middle here. Around 50 milliseconds you begin to see the digit, and very sharply after that you have enough evidence to see it. Okay. What's interesting also is that it's a sort of bimodal thing. We had this, you remember, cursor, so subject could say anything from not seen to seen, but it seems to be bimodal. You either see it very well or you don't see it at all, but in this task at least there is not many intermediate states. So this is great because we can place ourselves in the middle here, and about half of the trials are not seen, half are seen, and we can decide what difference it makes in the brain. So in this experiment we recorded brain waves millisecond by millisecond after the digit appeared on the screen. You can see what happens to a left target and to a right target as a function of time here in milliseconds. These are very well-known brain waves that are initially lateralized, P1A, P1B, the N1, which is this negativity here, then the N2 and the P3 waves. They are on the surface of the scalp, voltages that are evoked. And for each of them, we can ask how does their amplitude vary as a function of the delay between the digit and the mask, and does it resemble the visibility ratings of the subject? Okay, because the subjects tell us here, I don't see anything, here I see maybe on a very small fraction of times, and then they see more and more. So you can immediately see that the early waves don't fit the bill. For instance, the N1 here is very clear. You get a very, very strong N1, even to digits that people have not seen at all. The brain is activated. In these early stages, below 200 milliseconds, you get enormous activations without consciousness. And then it gets shaped, and progressively you see the shape resembles more and more the visibility. But it's only in this late period, around 300 milliseconds, that you get a brain activation which has this sort of all or none character, which resembles very much what the subjects report. So the bottom line is the early waves are largely unconscious. And we can see this in this reconstruction of the brain activity. What we can do is take these scalp recordings, return, using a model, of course, to the underlying brain activity. It's not very precise, you can see it as some errors, it's distributed, but we can then put a sort of virtual electrode and get the idea of the activation of a brain region, like this visual fusiform region here. And you see something very interesting. In this region there are two steps. One step which is linear as a function of the delay, and then another step which has this non-linear character, which resembles what the subjects report. And in the prefrontal cortex, we get almost only the second stage. If you look carefully at the curves, they are essentially at the bottom here with very little activation for the 33 milliseconds, this is the green curve, that you experienced at the beginning, where it was invisible. Okay. But the first wave here, early on in the visual cortex, is very strong already for this 33 milliseconds, only it dies a little bit later on. You have the idea of a sort of flip-flop system. The brain accumulates evidence initially, and then it either makes it over the threshold and gets triggered into a high-level state of activation distributed in many areas, including prefrontal cortex, or it dies, it is below the threshold, you do not get this sort of reverberating activity which self-amplifies, and the subject reports, I have not seen the stimulus. This sort of division we see in many experiments, and I wanted to show you a movie of what happens in another experiment, the attentional blink paradigm, where once again we have the same exact stimulus, it's a word in this case, and half of the trials the stimulus is seen, and half of the trials it is not seen. So, I'm sorry, this is a little bit dark now, maybe we could lower the lights a little bit, if it was possible. And on the top part of the screen you have the not seen condition, on the middle you have the seen condition, and here the difference. Yeah, if you could lower the lights on the stage, I don't know if this can be done. So this is the left hemisphere, great, thank you. This is the right hemisphere, okay. We'll start the movie. And the stimulus is entering at 0. Oh, did I stop it? Oh, oops, try that again. So now you begin to see a little bit of brain activity. I stop it at 100 milliseconds, where you can see there's a lot of bilateral occipital activity. This is where the early visual areas of the brain are. It's already beyond primary visual area here, and you see virtually no difference at all in these occipital areas between the seen and the unseen condition. If I start the movie again, I'm going to stop it a little bit later, maybe here. You can see the activity has progressed along the ventral visual pathway. Now it's more left lateralized. In the left hemisphere is, of course, where these orthographic representations of words lie. But once again, you see an enormous amount of activation. Just a few hundreds of milliseconds later, the person is going to say, I didn't see any word, there was no word. Okay? but she has this very strong orthographic activation in temporal lobe. Then I start the movie again, and you will see the divergence. The activity builds up and it gets stronger in the scene condition, and now it seems to explode. It enters into the inferior frontal cortex, goes into the more dorsal regions, the parietal lobe, and you can see the difference is that in the case of the unconscious activation, there is still activation, but it is confined to the temporal lobe and the occipital lobe. It doesn't get into these more dorsal, frontal and parietal lobe areas. This is just, of course, one example. We have many paradigms which show us a similar pattern of activation. In all of these paradigms, there is quite a lot of processing of subliminal stimuli, but the higher you go into the cortical hierarchy, the more the activation dies when it is subliminal, and the more it gets amplified when it is conscious, creating this large-scale difference in parieto-frontal brain system. And the areas change a little bit according to the content of the stimulus, whether it is a sound, whether it is a word, whether it is a picture. One of the most interesting studies was done here in Israel, and with collaborators in California by Itzhak Fried, Rafi Malar and collaborators. They've been doing several studies where single neurons were recorded in the human brain in epilepsy patients, and these single neurons in the anterior temporal lobe quite late after the presentation of the picture, such as the World Trade Center here, they fired spikes only if the picture was conscious, almost only. You can see a little bit of firing to the non-conscious picture, but then this enormous amplification and long-lasting pattern for the conscious case. There is a lot of convergence for this notion of a late global ignition invading the higher brain areas only when the stimulus is conscious. And we have many other signatures of consciousness that I want to mention briefly here. This is a study in my lab with intracranial recordings in collaboration with Lionel Nakache at the Salpêtrière Hospital in Paris. We recorded from 10 patients with intracranial electrodes, and we're able to show that the difference between conscious and non-conscious processing seems to be occurring always late, after 200, 300 milliseconds. It is visible here in terms of an increase in gamma power. The brain emits oscillations, and these induced oscillations, they may exist even when the stimulus is non-conscious. So you may have heard a while ago from Francis Crick and Christophe Kohr, there was this hypothesis that 40 Hertz or high gamma activity was causally related to consciousness. It's not quite true, because you can get this activity early on when you're not conscious. But if you get it late, amplified in this ignition pattern, then it's very likely that the stimulus was conscious. Same thing for synchrony. When the brain is processing information consciously, it synchronizes its brain areas. So two distant electrodes synchronize, and they tend to do so in the beta band, which is a lower frequency band, around 20 Hertz, where the brain exchanges signals at a long distance, and especially top-down. And then causal relations also increase. So you can see with this depiction here, graphic depiction of the causal relations, that long-distance causal relations increase, again late, about 300 milliseconds after the stimulus was presented, suggesting the brain communicates with itself. There is better communication across the long distances of the cortex when the stimulus is conscious. And this fits rather nicely with the predictions of a model that Jean-Pierre Changeux and I had developed also with Lionel Nakache, which we call the global neuronal workspace idea. The idea is very simple. Maybe, conscious perception is not so complicated after all. The idea here is that, of course, we know there is a lot of processing going on unconsciously in specialized systems of the brain, like these orthographic processors or this picture processor. Okay? They can do their job. They are little machines. They can do their job without consciousness. But maybe what we call being conscious is when the information has reached a stage where it is exchanged across areas of the brain. It is globally available. And there is a dedicated anatomical system for that, which is neurons with long-distance connections that interconnect the high levels of the brain. So this is represented here by this inner circle of areas that exchange signals with each other, creating this reverberating activity, explosion of high-level activity, ignition, which allow the information to be shared flexibly. It's just one slide. I could go on and show you some simulations. We can reproduce many, if not all, of the signatures that we are finding empirically with this very simple model of a reverberating activity late in the process. So, very simple idea, right? When we are conscious, what we mean by that is that the information has reached a stage which of course has a limited capacity, so only maybe one object at a time can be in there, but this stage where the information can be shared. And because of that, we can speak about what we saw, we can store it in memory, we can evaluate it, we can keep it in mind for a long time, a selective system that keeps the information. So this is one simulation actually of a sub-part of the system, of course a very core simulation. I hope we will be able to do much better with the development of the Human Brain Project, realistic simulations of cortical columns, but just a very simple idea, thalamocortical columns that are interconnected together to form a feed-forward and then a feedback system. And when we simulate such a system, one stimulus may climb the cortical hierarchy, create this feed-forward processing, and then if it is the first one to get in there, create this global ignition pattern where the areas reverberate, they keep the activation for a long time, even when the stimulus was very short. Whereas another stimulus that comes in just a little bit later, simulating this attentional blink situation, it gets propagated feed forward, but then it's blocked at the higher level. So I want to show you that we can go a little bit further than that and ask about specific processes of the brain. If this model is correct, at some higher level in the system, there should be stages of processing that are only possible if we are conscious. There should be a limit to what we can do non-consciously. And the limit should be the ability to share the information broadly and to use it for long-term processing. So we decided to focus on a specific process, which is error detection. How you know that you made an error. It's actually very interesting. When we do this sort of task, you know, you're asked to click right if it's larger than 5, left if it's smaller than 5. You click so fast that sometimes you make an error. But when you make an error without any feedback from the computer, you click the wrong button, you immediately know that you've made an error. Okay? And when you know this, there's a specific brainwave which has been called the error-related negativity, which comes from the front of the brain here, typically from the anterior cingulate or cingulate cortex. And this activity occurs just 50 to 100 milliseconds after you press the wrong key. Some people have called it, I'm sorry to say, the oh shit effect. You know, you click and wrong button. But this is very strange because the brain creates the first computation, clicks the button, and then the same brain knows better, knows that it's been making an error. How is this possible? Well, the idea that we are testing here is that this depends on consciousness. That if you are conscious, then maybe the unconscious process clicked the button, but then the conscious process is monitoring, revealing that you're making an error. So we decided to test this by the very same paradigm that I showed you earlier. We asked subjects to click left and right. We asked them to rate whether the stimulus was seen or unseen, and we also asked them whether they think they've made an error or not. And this is the beautiful finding. We saw the trials as a function of whether the subject reported seeing or not seeing the digit, and we find that there is an error-related negativity only when the subject reported seeing the digit. It's the same stimulus, but you have to say that you've seen it in order to get this error response. If this is a not seen trial, you get no response at all. And this comes from the anterior and posterior cingulate according to MEG source reconstruction. And we can even take the very same exact duration. So in this analysis, we separate this curve into the different durations of stimulus presentation before the mask appears. And you can see that the same colors can appear in the seen and the unseen case on the left and on the right here. If I could have my mouse, here it is. You can see this huge error negativity for 33 milliseconds on few trials where you see it, not when you don't see it, and likewise for 15 milliseconds here. It seems to be an all or none thing. If you see the digit, you can have an error negativity, you know you've made an error, you have this introspection in a sense. If you have not seen it, you don't have it. What could be happening here? Well, here's the interpretation. We have in the brain, as I told you, unconscious chains. And these unconscious chains are able to go from perception to action. And so when you click the button, maybe in part, in some trials, it is an unconscious process. You click the button before having completely analyzed the stimulus. And we can show that you can do better than chance, even in the unseen trials. Okay, but at the same time, on some trials at least, you have this higher level process creating this ignition telling you, you know, it is actually a number which is larger than 5, I should press the right key. Okay? And what happens is that these two representations, the conscious intention and the actual action, may not always be compatible. When you make an error, very often it's because the lower one has responded before the top one. So you can compare the two, and you can realize that you've made an error. The error detection is an internal comparison by the brain. So how could we test this? Well, I will show you a new way to test it, and it's a very powerful method that many brain scientists use these days, which is called multivariate decoding. We can take the brain signals and use them to decode what the person has in mind. What we do is we take a time slice of brain activity and train a computer machine learning system to sort out the trials into different times. And I'll show you different ways to use it. One way is we can use it to decode the stimulus. For instance, the digit can be on top, on the bottom of screen. We can train a decoder to decode where it was on the screen. But we can also train it to decide, even before the subject is clicking, is the subject going to click right or to click left? A decoder of the motor action. And we can also train it to decode what was the intention of the subject. Because we have error trials, the intention of the subject is not necessarily the same as the action, so we can separate the two. And finally, we can train a decoder to try to decide from the brain activity whether the trial was an error or whether it was a correct trial. Okay. So does the brain encode in its own activity whether it was an error or not? So according to this model, we should be able to decode the content of perception and of action on all trials, whether they are conscious or not. But the top level, sorry, I can't do this, but the top level here, intentions as well as error detection should only occur when you're conscious. So here is how this multivariate decoding works. You have a lot of information from the brain, like in this magnetoencephalography machine, we have 306 channels that give us insight into brain activity every millisecond. And we have also 256 channels of EEG, electroencephalogram. So we can take a slice of time, and in this slice of time we have all of these channels. We train a machine decoding system to tell us what was the state of mind of the subject. Was he clicking left or was he clicking right, for instance? Was he starting to click? We get a sort of time curve like this, where for a long time the decoder cannot do it, especially before the stimulus, even a little bit after the stimulus. And then you can decode it, and you can see how the information unfolds in the brain. It's a very powerful, interesting technique. At different moments, different decoders can be trained, right? So you can see how they unfold. So these are the results. Each of these is a curve as a function of time from the onset of the seen or unseen digit, and we see what we can decode. So first thing we can see, is that we can decode top versus bottom position on the screen. So even on the unseen trial, the subject says, you know, there was nothing, we can decode where it was. And we can see that it's sharply after the stimulus and then it decays. Okay. A bit later in time, we can decode what the subject is going to do. Is he going to press right or is he going to press left? Okay. And we see that it's a bit stronger on the seen trials, but it's also present on the unseen trials. But now look at the intention. We can decode the intention of the subject, but only on the conscious trials. On the unconscious trials, the subject doesn't know what he's supposed to do. That's the whole idea about consciousness, right? If you are conscious of the digit, you can program an intention. If you haven't seen a digit, the brain cannot have a conscious intention, so it doesn't know what it should have done, so it cannot correct its error. And the same, of course, is true, therefore, for the computation of the error. We can decode it later in time. The brain knows that it's making an error, doesn't know when it's unseen. It's very interesting that these events are all or none. They are really just absent when there is no consciousness. So all of that occurs while we can also decode whether the trial is going to be conscious or not. We can tell in advance whether the brain is going to see the stimulus or not. But this corresponds to a whole wave where there is an amplification of sensory information and uniquely conscious computations. So I want to finish this presentation by giving you an idea of where this is going in terms of the applications or implications of this work. First, I think there are maybe some philosophical implications. I don't like to talk too much about philosophy because I think this is beyond philosophy now. This has become an empirical field of research. We have really changed, I think, the way we should think about this problem. But it is it has a certain numbers of philosophical implications to be able to say that we begin to think we know what we are talking about when we speak about consciousness. But second, there are practical implications. It's not always easy when you have a non-verbal organism who cannot speak, cannot report about its mental states, whether it's conscious or not. And that's the case for infants, typically. This is my little nephew a few years ago. I'm ready to swear he was conscious. He was 2 months old. But how do you know? Maybe he could have reflex responses, they can gaze at you and blink, and you believe, you project onto this mind consciousness, but is he really conscious? How should we know? And likewise, for this person, of course, it's a huge problem. This person may still move, may still wake up in the morning, she's in a vegetative state, okay? In a vegetative state, you still have a sleep-wake cycle, so you wake up in the morning, you close your eyes at night, but during the day you don't respond at all, okay? You ask the person to blink, she doesn't do it. You ask the person to move their eyes, they don't do it, they don't respond to you. Sometimes they will just move and have an emotional display perhaps, but you still don't know whether it's conscious or not. How do you know? So the idea of signatures of consciousness is that if we could use these signatures, we look inside the brain of these people, we should be able to see whether they have a nonlinear response, whether they have this ignition pattern, whether they have brain scale communication that are markers of consciousness. So that's what we did in a recent paper last year. Sid Quider at the École Normale Supérieure, my wife, Dehaene Lambert, and I, we decided we could use these masking paradigms in young children. It's actually relatively easy. You can flash a face for a short duration, vary the duration, just like we do with the digits, precede it and follow it by a mask. And we just look at the brainwaves. We don't need the reports. So what do the brainwaves tell us? The brainwaves tell us that there is, just like in adults, there is a phase of linear accumulation of evidence. So you can see these waves building up in strength, accumulating the evidence from the duration of presentation of the face here. So all of these curves are for increasing durations of presentation. But then you also see that there is a late stage, which is completely all or none. The first 3 curves below 50 milliseconds are all at 0, and then all of the others are above 0. Or rather, in this case, negative. There is a negativity. It's very interesting that Sid Quider was also able to measure behavior in infants of the same age. These curves are for 12 months olds, but he also tested 5 months olds. And this is precisely the durations, when you get this negativity, are also the durations where the infant is capable of orienting to the face. If you present the face below this duration, the infant does not orient. Okay. So we have converging evidence. It seems to be that the architecture of the infant brain is already capable of accumulating evidence about a very short image and to get into this ignition pattern. What's very interesting is that it's much later than in the adult human brain. In the adult human brain, I told you it was around 300 milliseconds. It's a rough figure, it depends a little bit on the paradigm, but this is now around 1 second. 3 times slower. And in 5-month-old babies, it's even slower, on 1.3 seconds. So that's quite interesting to think that the baby may have the right architecture, but the brain waves are much slower, probably because the myelination of the system is not yet fully developed. So communication is very slow, the baby needs more time to accumulate the evidence, but ultimately he can be conscious, according to this data, of an external piece of evidence, such as a face. It just needs a lot of time. And I think it fits with our interaction with babies that, they seem to take in the evidence and then they may have a response. Now, question of the patients. I really think that this is the touching stone of this field of consciousness research. We know that there are many clinical classifications. These patients can be brain dead. This is not difficult to define. You have no longer any EEG responses for a long period. Coma, or still you have a lot of brain activity, so now in this case it's a bit more difficult to ask whether the patient is conscious or not, but he seems to be in a so-called deep sleep. Vegetative state, where I told you that there is still a sleep-wake cycle, so the patient wakes up in the morning but doesn't respond. Minimally conscious state, the clinicians use this category where the patient sometimes responds. Unmistakably, you ask him to move his eyes and suddenly for a second he seems to move his eye just at the right moment. But this happens once, twice, but on many occasions it does not happen, so there is a lot of fluctuation. And finally, as you know, there is this terrible condition called locked-in, in which the patient can be in fact fully conscious, completely aware, intelligent, able, for instance, to dictate a whole book, as was the case for Jean-Dominique Bobby, who wrote this incredible book, The Butterfly and the Diving Bell. And what happens is that these patients are disconnected from virtually all bodily responses, voluntary responses. He dictated his book by a blink of the eye, of the eyelid. So, but we think that there may be patients that are complete locked in, that are not even able to bat an eyelid, and therefore they may still be conscious. So can we provide better definitions of these states? The clinicians have a hard time because all they have is behavior, and a few reflexes and so on. Can we have better predictors? So there was this very important paper by Adrian Owen in Science 2006. Many of you may have seen this, where they showed that you could take a patient in an apparent vegetative state, and if you did an MRI and you asked the patient, first of all, to listen to speech, what they showed was that this is a single case, 1 out of 60 patients initially. But this patient had extensive activations, just like the controls, when she was listening to speech. Then they did something daring. They asked the patient, they began to speak to the patient, and they said, well, okay, for the next 30 seconds, please play tennis in your head. For the next 30 seconds, please imagine that you are visiting your apartment. And what they saw, to their utter surprise, was that there was still cortical activity, even though you can see the brain is damaged, there's still cortical activity differentiating these two conditions, and at roughly the same spots as in the normal human brain. They concluded the patient must have been conscious, and that she was vegetative only in appearance, suggesting these patients exist. And the problem with this methodology is that it's very difficult to do more than one MRI in these patients. Already one MRI is difficult because of all of the technology surrounding these patients. But it's costly, you can't use it to communicate with the patient. So it's even more terrible to think that you did that once, you think you realized that the patient was conscious, and then you let the patient return to his bed, right? So we believe that EEG is going to be the solution. And EEG is a very simple technique where with just a few electrodes you can record brain activity in real time with a lot of temporal resolution. And if what I said is correct, we should be able to monitor brain activity, and from especially the pattern of long-distance communication, this ignition of long-distance communication, we should be able to say something about the state of consciousness of the patient. So we decided to work on this problem with Jean-Remy King, Jacob Ossit, and my colleague Lionel Nakache at the Salpêtrière Hospital. And last year we published a paper with a new idea to measure brain scale communication. We'd like to measure how much communication there is between region X and region Y in the brain. We have these EEG signals, and the idea here is we're going to decompose them into symbols, which are defined by the way the signal evolves, in this case over 3 samples, separating by a critical time. Okay? So 3 samples, there might be 6 possible orderings of these measurements, decreasing, V-shape, and so on and so forth. Now you may have such measurements at 2 distant sites, and now what you can do is count the co-occurrences of these signals and compute a quantity which is called symbolic mutual information. Just how much mutual information there is between these sites. Now there is a problem here, which is that maybe there is mutual information not because these 2 areas are communicating, but because they have a common source. There might be a source in the middle that's creating these 2 signals. But we found a new way to discard that, which is to eliminate the components of this matrix, which are the trivial correlations between symbols. So for instance, the 2 signals are decreasing. This could come from a common dipole, with these 2 electrodes being sensitive to the same brain area. Also, if one is increasing, the other is decreasing, this could come from the same dipole. But all of the other symbols, they are non-trivial, okay? And we can still compute a proxy for symbolic mutual information. We call it weighted symbolic mutual information from this measurement. Now, enough mathematics, but this is the final picture. We had a lot of vegetative patients, minimally conscious patients, conscious and healthy subjects, and you can immediately see when we compute this measure of mutual information across the brain, each of these colors along an arc represents one measurement of symbolic mutual information. There's a clear difference between the vegetative patients on average versus all of the other ones. Okay. We have a measurement which is becoming sensitive to consciousness. And it's very interesting that it appears to be an impaired functional connectivity, especially at the medium and long distances over the scalp. So this is in centimeters, the distance between the electrodes. At short distances, we are not sensitive, but as long as the distance is large enough, we can see a very sharp difference between the vegetative state patients and all of the other ones. This is true regardless of the etiology of the patients. It is also true regardless of the delay between the insult and the measurement. Now, as I told you, we have the clinical diagnosis and we have the brain measurement. And I don't think there is a gold standard. You may think that the clinical label is important, but the clinicians have a hard time. So can we do better, maybe? So here what we do is we train a machine learning algorithm to use this WSMI measure as well as many other measures of brain activity to try to see if we can mimic the clinical label. So the clinical label is vegetative, minimally conscious or conscious, and we have now the automated machine learning label. And you get the idea that the diagonal is hot and the far from diagonal is low, which means that we do much better than chance. But we are not perfect. We are not perfect for several reasons. One of them, of course, is that the measurement is not perfect. But we are not perfect also, perhaps, because there are some patients that are misclassified. So we take the vegetative category line here, and you see the majority are also classified by our machine as vegetative, but some are classified as minimally conscious or conscious. What happens to them in the future? If we follow up for 6 months, this was done by Lionel Nakash, you can see that many more of those that had signs of being conscious according to machine learning recovered, and compared to a very small fraction of those that were consistently labeled as being vegetative. So it's a beginning. It's not perfect. We would like it to work on every single case, and it does not work yet on every single patient. So it's not sufficient for the clinic. It's a beginning. It says that there are enough traces of consciousness in the brain measurements that we can use them for the clinic. So I think I'm reaching my conclusion now. I think that we already have a concrete proposal for consciousness. And what we call consciousness may simply be the global availability of information. There is a machine running that makes some of the information a selected bit, the one that we attend to, this button. We attend to it, and the information is made globally available to many brain systems.
To many what?
To many brain systems.
Brain systems.
Right. So, I just read what I've written here. We have a lot of non-conscious, specialized processors in the brain, but we also possess a special and probably evolved system for distributing the information, what we call the global neuronal workspace. And the goal of this system is to break the modularity, take information from one processor, make it usable by the others. So this requires amplification, holding online the information, routing it to other processors. Property that we don't fully understand yet, but we think that's the goal of this system. Now, the brain mechanisms of this workspace is being increasingly understood. It's related to a temporally or metastable state of distributed neural activity. It has this property of sudden ignition. We think that there is a subset of neurons that self-reinforce each other, sustain each other, and create this divergence to a high state of activity. And they are especially dense in the parietal and prefrontal lobes. And this creates in turn several characteristic signatures that we can pick up on the scalp. In the end, it may be surprising, but it's not so difficult to see whether the brain was conscious or not of a piece of information, because the brain signals are large, because it's a large distributed system. So this representation is even becoming decodable, and I think it's important for the general public to be aware that more and more we can decode brain signals to return to their meaning in terms of psychological states. Did the person perceive or not? Did she have this intention or not? We can more and more decode it. It's more of a demonstration of principle for the moment, because we show that we can do it better than chance. So instead of being at 50%, which is chance, we can do maybe 60, 65%. It's not good enough in practice to guess at somebody's mind, but it's a proof of principle that the code is there. And this knowledge is now applicable in neurology, in pediatry, and I have not spoken about it, but also in psychiatry. It's very interesting to ask whether there are some diseases of this global neuronal workspace And my lab is working on the hypothesis that schizophrenia in particular may be a disease specifically affecting these long-distance networks and creating difficulties, especially at the level of conscious processing. It's just a hypothesis, but we have some data for it, and we could discuss it. So I just close with this picture of the many people who contributed to this work, but especially Lionel Nakash for the patients with Jacobo Sitt and Jeremy King, my wife Ghislaine with Sid Quider for the babies, and I just want to mention that I just published 2 weeks ago a book in English called Consciousness in the Brain, which is summarizing all of this data. And thank you very much for your attention.
Thank you very much for a fascinating lecture. Are there any questions? Yes, please.
Did you try looking for such a global workspace in animals?
Yes, we are starting, in fact. So we are doing experiments in monkeys at the moment in the lab, and some of the paradigms have been used, like masking has been used in the monkeys. We are also using the same paradigms, especially for resting state measurements of resting state activity in the monkey. Yeah. And I believe there is a long history of this workspace system. The parieto-frontal system has been well characterized in the monkey. The so-called working memory system is very close. It's essentially, we're talking about the same thing. So what may be particular, of course, in the human brain is this additional introspection or reverberating activity turned onto itself. So, and the role of language here, of course, may be particular. But the basic operation, especially this notion of a linear accumulation system and then a non-linear, it's present in animals, basically.
Yes, please.
I got two, if I may. The situation with the bottle that we didn't see before you pointed at it is obviously different from this temporal paradigm that you described. So, do you think the mechanisms are more or less the same in both cases? And the second question, okay, there's this object that goes into my brain, but I don't see it because it doesn't make it into the consciousness. Can this object affect my conscious behavior and conscious decision making later on?
Very good question, thank you. Yeah. So the first question, the mechanisms of inattention are actually very much what we were studying in some of these experiments. So I went very briefly over this attentional blank phenomenon, but that's exactly what it is. We distract you, and then you don't see the bottle. But if there was not this distracting task, the bottle is perfectly visible, and in this case the letter is perfectly visible and you see it. So it is a sort of all-or-none blocking by a distracting task. And this is perhaps the best paradigm that we have now, because this is the one in which the stimulus by itself is not affected. It's very strong. It could be conscious. The only reason why it's not conscious is that your mind is oriented elsewhere. Your workspace system is oriented elsewhere. So this is where we see the sharpest boundary. All of the initial processes, the movie I showed you was of this kind. All of the initial processes are identical, and then there's one moment where it becomes dramatically different. It's like a gate in the system, and many of us operate under Mike Posner's idea that attention acts like a gate that makes the information enter into consciousness. So with respect to your other question, can consciousness really influence deeply our decisions? This is still being debated. Most of these effects of priming are short-lived, and that's consistent with the brain activity I showed you. It can shoot up quite high, but then it decays. And after 1 second, there's not much left, basically. So if you take an immediate decision, it can be above chance. If you have a delay, 1, 2 seconds, typically the response falls back to chance. So there is not much of a long-term influence. And that's also a word about publicity. You know, people were thinking about using subliminal images for marketing. It doesn't work very well. The effects are minuscule. The marketing people much prefer to have a conscious image, which is very striking. So the effects are very small. There are some rare experiments where there is learning of an unconscious stimulus. So the unconscious stimulus is sufficiently present in the system that it affects learning, and it may affect your value system, for instance. So these are the only experiments where there may be a long-term effect. If you're repeatedly exposed with an unconscious picture, you may end up preferring it over one that has never been presented. But again, these are very small effects.
Israel?
Your conclusion was that consciousness is what we call is that it is the global availability of information. That's the conclusion.
Right.
What do you start with? What does the word consciousness mean to you?
Okay, I think that's part of the problem. We have to define it, right? And there are multiple meanings in everyday life. So I was talking exclusively about this meaning of access to information. Access.
Access.
Access. So if you think of how we use the word conscious in language, we typically say he was conscious of this piece of news, or he was not conscious. You know, he was not conscious that the bridge had been destroyed and the road would be blocked. Okay, this is what we call the transitive meaning of consciousness.
The what? The cognitive.
Transitive.
Transitive.
Transitive, because there is an object that you can or cannot be aware of. Okay, there are many other meanings. There is
Awareness.
Maybe you call it awareness. Okay. Yeah, I looked in the dictionary and at the use of this word. Some people use awareness in this sense, and they think it's a sort of lower level meaning. But I looked at the dictionary, it's not true. It's been used all over the place, awareness, consciousness. It's just confusing. So we talk about conscious access. That was the only object of this lecture.
Any other question? Well, if not, I would like to thank you again for really a fascinating talk.
Thank you.
You know, I don't know anything about this, but it's really opened a lot of questions in my mind, and maybe I will have a chance to talk to you about it when we meet in Rehovot in the next few weeks that you are here. So thank you again for coming, and I thank you on behalf of the Israel Academy of Sciences and also of the Institute de France and the French Embassy, that we are all partners in inviting you here and giving this talk. So thank you very much.
Thank you.